All right, welcome back. We're talking about special solutions for our evolution equation for curves, and we're going to talk about some issues. Okay, last time we had these special solutions. We talked a little bit about how there's this special solutions given by horizontal lines, and there are many of them. And our goal is to show that these are like a ball in a bowl, and they're stable in some way. It's not exactly a bowl because, you might perturb one of these and then flow to a different one. That's okay. That makes it quite complicated in terms of the mathematics. But we're just trying to work through an intuition here. We talked about circles. They're not going to cause us any trouble because they are ruled out by the boundary conditions. We talked a little bit about the rectangular elastica. They are going to cause us some trouble. They are not flat lines, and there are infinitely many of them. So we're going to have to rule those guys out. Okay, and then we gave this little bit of a nightmare. So a nightmare situation where you connect together two arcs of circles by something like a transition in the middle. And this transition could have a variety of shapes. One possibility is that we use a piece of the lemniscate of Bernoulli, and this might shrink. If it shrinks, then we might end up with something that is irregular, and we might have a very exotic kind of singularity. That would be a nightmare. So we don't like this. But what I promised you was that we would talk about something more straightforward, a more fundamental obstacle to stability of a horizontal line segment. Now, I've already written these slides down, but I lost the recording, so I'm going to use a little trick where I can redo my writing to, I don't know, see how this works. Okay, so we're going to call this stability of lines. Look at that straight line. Okay. So here we go. Issues. First, rectangular elastica, like we talked about. Then we have the complex transitions. We talked about those. And now something more obvious. We're going to call this topological. So let me explain what I mean by topological. You might have heard the word topological before. If you know what it means, great. But if you don't, just think about it as being like a type of categorization, a class. Something that's like it's a property of your curve that is preserved under small perturbation. And I'm going to show you what I mean. So let's take our parallel lines and then draw something that's, I don't know, almost straight. That can turn into this, and that can turn into this. Okay, and these are all in the same topology. They've got the same basic form. Now, what it can't do is it can't turn into that. Right? This would require some kind of singularity, some kind of terrible change in the geometry of the curve. Something that's not smooth, and we don't want that to happen. It also can't develop a little hook like this. If it did that, then it would have to have violated the boundary condition at some point. It would be discontinuous at the boundary points. This is also impossible, right? So you've got this tangent vector coming around, and you see that in this one, it's pointing the same direction at both ends, and here as well. But in this second one, you can see that it's made this little loop-de-loop, and so the total amount of angle that it's turned through is larger. Okay, so we encapsulate that idea in terms of this symbol, winding number, omega. The top one has omega equals 0. The next one is omega equals 1. And this one here, it turns through half of a circle, so we say omega equals 1/2. And that's a special feature of these kinds of curves, that you can have fractional, or actually just halves, a winding number. All right, so you've got it. In general, you have m/2 as your winding number. Here, m is an integer, so we use this z symbol for an integer. And now what this red arrow is trying to say here is that you can't go down in this picture. You can't go from this perturbation of a straight line down to this loop or the hook. But also you can't go back. You can't go back. So if you perturbed, if you changed somehow your initial curve to be one of these, then it's definitely not going to evolve back to a straight line. That's not going to happen. That is impossible. So whatever assumption we need to make, it needs to either implicitly or explicitly ensure that omega equals 0. Yeah. Okay, need omega equals 0. All right. So we'll call this A1, assumption 1. What do we need to make our result possible? Our goal possible, stability of lines. Okay, so we need omega to be 0. And here I've given a formula, a recipe for calculating omega. And we're going to see this guy come up again later. But this is an integral adding up the value of the curvature scalar. This is a measurement of how much the curve is bending at each point into or away from its normal. And ds is the parameter along the curve that measures exactly how long the curve is. So if s equals 0 on the left-hand endpoint, if you get to s equals 1, then that is like the length of string equal 1 if you stretched it out straight. Okay? That's like a straight line length. That's called the arc length, and it's going to be very prominent, so get it in your mind. And the fact that this is a recipe for the winding number, this is a good thing to learn in a differential geometry subject of curves. And I hope that either you go look up one of those or download some notes or something. This is a beautiful subject. Okay, second assumption. We need to rule out these complex transitions, and in other words, what we can add the complex transitions in the rectangular elastica. How can we do that? Basically, if you look at these guys, here it has this kind of S shape. Here it has also a kind of S shape, but it's very special. It comes up to a vertical point. There is no rectangular elastica that does not come up to a vertical point. There's no sort of flat rectangular elastica. It doesn't exist. And by the way, we're very sure about what elastica exist or not because they've been studied and classified quite completely. So you can look at work of Linner, who has the free elastica case completely classified. Okay, so let's look at this. So here we've just looked at the tangent vector, and you can see it's going through these oscillations, and if we draw this down here, we can look at sort of how much total turning, using this formula, the tangent vector goes through. Of course, for this curve, the winding number is 0. So the total turning will be 0, but we can sort of be a bit sneaky about it and take the absolute value, because here up to here you go through pi over 2, 1/4 of a circle of a turn in your tangent vector, exactly, because that has to be vertical, the rectangular elastica in the midpoint. And then it goes back exactly pi over 2. So total is pi, but that's not going to be this total because k is positive and then negative. It's going to be this total. So this quantity with the absolute value is the one that is going to be pi. So if you assume it's less than pi, that is probably pretty close to an optimal assumption. It's not exactly what we would conjecture to be optimal, but it is pretty close. And it's certainly better than what we can do. Okay, so does that work? And now what? Well, I already gave it away. That is better than what we can do. Actually, what we have trouble with this quantity. The reason we have trouble with this guy is that this is an absolute value. And absolute values are, if you graph them, they look like sharp points at the origin. And that's because and that means that at the origin, when k is 0, it's not differentiable as a function. And although that can still be dealt with in some ways by approximation and so on, for us and these flows, we don't know how to make that work. So we use a different approach. We go around the corner. We go around the back way. And what do I mean? Well, we take this quantity, L times integral k squared ds. And you might say, what on earth does this quantity have with this one? Have to do with this one? Well, okay, so so I introduced this notation here. So you use these double bars with the 2 and 2. That just means this integral, right? So the bottom 2 is the power of the integrand, and the top 2 is there because this integral would be to the power of 1/2 normally, because that would be the norm, something we call a norm. But we don't want the integral to the power 1/2, we want the integral to the power 1, and 1/2 times 2 equals 1, so that's why there's a square there. If I'm being careful, I write the ds because the ds is not actually a flat measure, it's a weighted measure, and I'll talk more about that later, but sometimes it's good to put the ds there to distinguish it from a flat L2 norm. Okay, so shrinking that down using the power of technology, we can talk about why on earth this would be a good idea. How is this going the back way? Well, because, okay, this first integral here, it's like a power 1, right? This is the L1 norm, using this notation that we just introduced. And we can use something called the Hölder inequality. The Hölder inequality lets you control an integral by a product of integrals. If you've never heard of it, don't stress about it. If you have heard of it, good for you. That's what we're going to use. And if you know your stuff, then what we're doing is using p equals q equals 2. And as the product, we're just using the curvature, the absolute value of the curvature, times 1 as the two numbers. Two functions. Okay, and then we get length to the 1/2 and the L2 norm of the curvature. And if you look at this, this is exactly the square root of this quantity. So writing in green, if we had that was less than or equal to c, then this would be less than or equal to the square root of c. Okay. So basically we choose c equal to pi squared, and then we would have definitely, because of this estimate, the total turning smaller than pi. Right, so that's this assumption. Okay, so this discussion, this talk about special solutions, it can go on for a long time because there are lots of things to say. But basically, the message that I'm trying to get across is that by considering these simple considerations, by taking into account these facts, it motivates an assumption on LK squared. That's what it motivates. It's necessary. It's a necessary thing. You cannot get away with no assumption. You cannot prove the result by just assuming omega equals 0. And a good choice for the bound would be pi squared. So let's see what we can actually do. What I am promising that I will show you that we will do. Okay, theorem. In mathematics, we call true things theorems. All right, so we're going to write down our flow. This is the notation that we use. So let me explain it slightly. Gamma is the name of the evolving family of curves. Here is the spatial parameter domain, which we sometimes call U. We're going to call it U later. And then here is the time domain. This capital T has a special meaning. It's the maximal time of existence. It's the time of existence up to which the flow cannot exist any longer. Smooth flow cannot exist any longer. And it could be infinity. We want it to be infinity, just to be clear. If it started off as a flat line, then it would not move. And the capital T would be infinity. Okay, and then the codomain, where the curve actually sits, these are the inputs. Okay, these are the inputs, and this is the output. So where the curve actually sits is the flat plane. That's why it's R2. Okay, so we're going to let gamma be a curved diffusion flow with, okay, here we go, the big reveal, the initial. So it's very important that we're only assuming a condition like this on the initial data. Okay, now this is assuming, so imagine the bowl analogy or the trough analogy. You're perturbing your ball, and this is telling you how much. How much can you perturb? You move the initial ball, you move the initial data, this much in this space, then you're okay. Too much? We don't know. But we're saying this much, it's okay. All right, let's see what it is. 2 pi over 9. So no, we can't do pi squared. Pi squared is much bigger than 2 pi over 9. But good news, it's not a small number. It's not like 1 divided by a billion. Anyway, you will see where this number comes from. Okay, that's curved diffusion flow. What about the free elastic flow? For the free elastic flow, we do L k squared, the same thing. And actually, this is the elastic energy. So there's something going on with this quantity. It's a very nice quantity. Again, initial assumption. What can we do? Well, we can also do less than or equal to here. Not 1. It's not 1. It's pi. So that's good. That's pretty good. We are pretty happy with this pi. It's not pi squared. We think pi squared is true. But it's not pi squared. But pi is pretty good. 2 pi over 9 is not as good. Okay, now what's the conclusion? First, the flow exists forever. Nothing bad happens. It just flows forever. Where does it go? Does it just go off to infinity, or does it settle down? What does it look like? We want it to look like a flat line. And it does. Gamma converges to a horizontal line. And now this means that, okay, the points converge. So each point moves to a horizontal line. But also the tangent vectors converge. The derivative of the tangent vectors, the curvature vectors converge. Everything converges. All the derivatives of gamma converge to what you would get on a horizontal line. So at every scale, you can think of this as a very, very fine convergence, almost the best convergence you could possibly hope for. How fast does it converge? I'm glad you asked. Exponentially fast. And that's also really good. That's really what you want. Okay, so make a little comment, and then time is definitely up. You might ask yourself, where is this omega equals 0 assumption? Well, it's basically here. So if you look at this calculation here with the k, the omega, recall it's a multiple of 1/2. And here we've got the integral of k smaller than the square root of this quantity. So that means that it's smaller than the square root of this. Okay, and then divided by 2 pi. But there aren't many numbers between 0 and 1/2 that have that property. So if you work it out, and please work it out as an exercise for the interested viewer, then you will see that the only possibility is omega equals 0. Now that's a long way of saying that this is actually an implicit assumption. So we are assuming it. we are assuming that omega equals 0. Okay, I think that's all I want to say. So this is the main result. This is what we're going to be focused on establishing, and I will try to give you a really good idea of where these numbers come from and what kind of mathematics is involved in proving something like this. Okay, that's it from me. Take care of yourselves. Thank you for your attention, and I'll see you in the next one. Peace.